Let's continue with this pattern and look at cubic interpolation. A cubic polynomial has four parameters. They are the constant term, the linear term, the quadratic term, and now the cubic term. So given four data points, x1, y1 through x4, y4, with all of the xi's distinct from one another, there exists a unique choice of parameters, a0 through a3, such that this cubic polynomial evaluated at the individual xi's will equal the corresponding yi's for all of these 4 points. Here's an example, and there are the 4 data points. Connecting them is this interpolating cubic polynomial. Writing out the 4 equality constraints in matrix vector form yields this familiar expression. Instead of 3 rows, 3 columns, and 3 unknowns, as we saw in the quadratic case, there are 4 rows, 4 equations, and 4 unknowns for this cubic case. Again, it can be thought of as ax equals b. A and b formed from the data, and x consisting of the unknown coefficients of the cubic polynomial. The pattern is clear, and generalizing this to higher order is simple. An nth degree polynomial has n plus 1 parameters, a0 through an. Given n plus 1 data points, x1, y1, all the way through xn plus 1, yn plus 1, with all of the xi's distinct from one another, then again there exists a unique choice of parameters, a0 through an, such that the nth degree polynomial evaluated at each of the xi's equals the corresponding yi for all of the points. Pictorially, that looks like this. Here there are actually 8 points, and this is the 7th degree polynomial that interpolates those 8 points. I solved these equations in MATLAB setting up exactly this array. The square matrix A, which is 8 by 8, the B vector consisting of the Y data, and then solved for the unknowns and simply plotted that. So we've seen this now from linear to quadratic to cubic and actually to nth order. Maybe is this all there is to interpolation? Given n plus 1 data points, just use an nth degree polynomial to interpolate and use that to predict values in between. Turns out this is probably not the place to stop. Let's look at this data that's shown here. I'm going to make a small change in the 4th data point, leaving the other 7 data points exactly the same. Let's move the data point to this location that I've indicated with a plus sign. Following the same mathematical strategy, let's see what that interpolating polynomial looks like. And it is this red line that I've just drawn. Notice that even though we only made a change in the data at one location, the interpolating polynomial is quite different at many of the other locations, including locations quite far from where the data was changed. How about if we change the data point down to this black X sign? Well, again, the interpolating polynomial takes on quite a different look than the original interpolating polynomial. So what we're noticing is that for these large degree interpolating polynomials, there's quite a bit of sensitivity to the interpolating function's value between interpolation points to the particular value of some data points. Here, when we change the data point y4 by just a small amount, the value of the interpolating polynomial between, say, x1 and x2 is quite sensitive to this value y4. Let's look at this another way. Here are 4 graphs of polynomial interpolation. A 3rd order through 4 points, a 7th order through 8 points, an 11th order through 12 points, and a 15th order through 16 points. Notice the kind of very unusual behavior that we're getting near the ends for the 11th order and 15th order, and even a little bit for the 7th order. Notice that the value predicted between the 2 points near the left end is quite different than the data itself. So what we're noticing is that for large values of n, the polynomial that interpolates the data tends to have large oscillations near the endpoints. In that sense, the behavior of the interpolating function between these points is somewhat unexpected and certainly non-intuitive. It doesn't reflect what we would have maybe drawn in by hand with the data. It turns out, let's say for simplicity, for evenly spaced x, the prediction, in other words, the interpolating polynomial's value, at the midpoint between x1 and x2 is highly sensitive to the y data in the middle of the data set, say y at I equal n over 2. I made a table of exactly what these sensitivities are. N equal 5 up through n equal 15, and the sensitivity ranges from 1.2 to 72, and notice how abruptly it's changing as n is increasing. This represents the derivative in the interpolating polynomial's value at the midpoint between x1 and x2 to the value y at n over 2. So in the 15 case, it means that if the eighth value of y changes by 0.1, then the value of the interpolating polynomial between x1 and x2 will change by 72 times 0.1, in other words, 7.2. So the interpolating polynomial is extraordinarily sensitive to some of the y's data, and the y data that it's sensitive to is quite far away. We saw this behavior exactly on the previous slide. So for this reason, polynomial interpolating functions using large N are generally thought of as bad predictors. This high degree of sensitivity of a polynomial's value at one point to its particular values at other points far away in the domain is one of the traits that makes polynomial interpolation with high degrees undesirable.